Now in this lecture we'll answer on two questions. In the first question we'll find out the area of this semicircle that is inside quarter circle AOB, and in the second question we'll find out the area of this green shape that is inside rectangle ABCD. So we'll start with the first question. In the drawing we have quarter circle AOB. Inside this quarter circle AOB we have this semicircle, and we know that AO equals to 5 units in its length, and our mission is to find out the area of this semicircle. So first of all we define the center of this semicircle. This point is point C. We define the touching point of this quarter circle with this semicircle. This point is point F. We define the intersection point of this semicircle with this quarter circle. This point is point G. Likewise, we define the point of tendency of tangent AO with this semicircle. This point is point H. And finally, we define the point of tendency of tangent BO with this semicircle. This point is point L. In the next step, we will define the radius of this semicircle as x. Therefore, CF equals to CG, they are both the radii of this semicircle, that equals to x according to our definition. So CF equals to x, CG also equals to x. And we actually know that the radius of the quarter circle is 5, because AO equals to 5. In the next step, we join point C and add together by a straight line. CL is the radius of this semicircle, that equals to x according to our definition. Likewise, we will join point C and add together by a straight line. So C edge is also the radius of this semicircle, that equals to x according to our definition. So we can implement here rule 1, because we have the radius C edge of this semicircle that equals to x is drawn to point H, that is the point of tendency of tangent AO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HG. If AO is perpendicular to HG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CL is equals to x. The radius CL of this semicircle is drawn to point L, that is the point of tendency of tangent BO with this semicircle. Whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LG. If BO is perpendicular to LG, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule, rule 1. So by doing those two constructions, we can deduce quadrilateral C edge OL. Inside quadrilateral C edge OL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces angle must be equal to 90 degrees in its size. So inside quadrilateral C edge OL, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral C edge OL that has 4 right angles as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle C edge OL, side C edge, must be equal to the opposite side OL. But C edge is X, therefore OL must be also equal to X. Likewise, according to the same rule, in the same rectangle C edge OL, side CL must be equal to the opposite side OH. But CL is X, therefore OH is also X. So if we found out that quadrilateral C edge OL is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Each side of this square is equal to X. Okay, so in the next step, we join points O and C together by straight line. By joining points O and C, you can do the right triangle, triangle CLO. Right triangle CLO is also an associated triangle because CL equals to LO equals to X. So in the next step, I'll copy the right and associated triangle CLO in a new page, and we'll implement the Pythagoras theorem on this right and associated triangle CLO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here by PT is a relation for Pythagoras theorem. So actually, this is the right and associated triangle CLO that according to the original drawing, according to the Pythagoras theorem, in this right triangle CLO, CO squared, that is the square of the hypotenuse, must be equal to CL squared plus LO squared. So I write it down. So CO squared, that is the square of the hypotenuse, must be equal to CL squared plus LO squared. CO is the missing side, so we leave it as it is. So CO squared equals to CL squared. CL is X, therefore CL squared is X squared plus LO squared. LO is also X, therefore LO squared is X squared. So in total, we should find out that CO squared equals to X squared plus X squared, this is 2X squared. So CO squared equals to 2X squared. Here we take a root out of this equation and find that CO equals to the square root of 2 times X units in its length. So here, this is 97CO, that is equals to the square root of 2 times X units in its length. We know that point O is the center of the quarter circle. From the center of the quarter circle, that is to say from this point O, we have line segment OC that bisect chord FG. Why line segment OC bisect chord FG? Because we know that CF equals to CG equals to X. So each half equals to X. So 97OC, that is one from the center of the quarter circle, bisect chord FG. And therefore we can implement here rule 7. So I repeat quickly on rule 7. According to rule 7, if a line segment is one from the center of, if a line segment that is one from the center of the circle bisect the chord, then the line segment is perpendicular to that chord. So in the drawing we have a circle, and this is point O, that is the center of this circle. From the center of this circle, that is to say from this point O, we have line segment OM that bisect chord AB. That is to say MA equals to MB. And because of the fact that line segment OM bisects chord AB, line segment OM will be also perpendicular to chord AB. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 7. So whenever you draw from the center of the circle a chord that bisects, whenever you draw from the center of the circle any line segment that bisects a chord, then that line segment will be also perpendicular to that chord. So we can actually implement this rule 7 in our drawing. Why? Because in our drawing, from the center of the quarter circle, that is to say from point O, we have line segment OC that bisects chord FG. And therefore, according to rule 7, line segment OC will be perpendicular to chord FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 7. In the next step, we join points O and F together by straight line. We know that the radius of this quarter circle equals to 5 units in its length. So what is the definition of line segment OF? Line segment OF starts from point O, that is the center of the quarter circle, and ends at point F, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OF is the radius of this quarter circle, that is equal to 5 according to what is given us the question. So OF equals to 5 units in its length. So in the next step, we copy the right triangle CFO in a new page, and we will implement the Pythagoras theorem on this right triangle CFO. Here by PT is the derivation from Pythagoras theorem. So actually, this is the right triangle CFO, that I got from the original drawing. According to the Pythagoras theorem, in this right triangle CFO, the square of the hypotenuse must be equal to the sum of the squares of the perpendiculars. The hypotenuse is FO, therefore the square of the hypotenuse is FO square, and FO square must be equal to CF square plus CO square. So I write it down. FO square, that is the square of the hypotenuse, must be equal to FC squared plus CO squared, according to the Pythagoras theorem, of course. So that produces FO equals to 5 units in its length, therefore FO squared is 5 squared, that is 25. And it is equals to FC squared. FC is x, therefore FC squared is x squared plus CO squared. CO is equal to 2 times x, therefore CO squared is equal to 2 times x squared, that is actually 2x squared. So in total we can find out that 25 equals to x squared plus 2x squared. X squared plus 2x squared equals to 3x squared. Here we divide this equation by 3, and finally we get that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. So what is the area of the semicircle? We know that the radius of this semicircle is x. Therefore the area of this semicircle will be equal to pi x squared over 2. So I write it down. The area of the semicircle equals to pi x squared over 2, because x is the radius. So it is pi over 2 times x squared. And just right now found out that x squared equals to 25 over 3. Therefore we substitute x squared in this equation by 25 over 3. We do it now, we get that the area of the semicircle pi x squared equals to pi over 2 times x squared. X squared is 25 over 3. So in total we can find out the area of the semicircle equals to 25 pi over 2 times 3, that is 6. So the area of the semicircle equals to either 25 pi over 6 square units, or in terms of numbers it is equal to 13.09 square units. Repeat again, we should find out that the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers it is equal to 13.09 square units. So we finished with the first question. In the next step I will present you the second question, and we solve the second question. So our mission in the second question is to find out the area of this ring shape. So in the drawing we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle ABCD we have this semicircle and this quarter circle, and they touch each other externally at this point. So we will define the touching point as point S. Likewise, we'll define the center of this semicircle, this point, as point O. We will define the radius of this quarter circle as x. So BC is the radius of the quarter circle, this quarter circle, and according to our definition, it is equal to x. Okay. We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side BC must be equal to the opposite side AD. But BC equals to x, therefore AD must be also equal to x. AD is not only one side of rectangle ABCD, but AD is also the diameter of this semicircle. So we actually know that the diameter of the semicircle AD equals to x. So if the diameter of this semicircle equals to x, the radius must be equal to half of it. So the radius must be equal to x over 2. So the radius of this semicircle equals to x over 2 units in its length. That is to say, OA equals to OD, the above the area of this semicircle, that we just right now found out, that is equals to x over 2. So OA equals to x over 2. OD also equals to x over 2. We know that all the angles in any rectangle, all the angles inside any rectangle are right angles. So this is angle ADC inside rectangle ABCD. That equals to 90 degrees in its size. So here we have an external notch between this semicircle and this quarter circle. That is to say, they touch each other externally at this point, point S. And whenever you have an external notch between two circles or semicircles, you can implement rule 10. So I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, in the drawing we have two circles, they touch each other externally at point P. So if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. The center of this circle is 0 at point O. The center of this circle is 0 at point M. And the straight line that connects their centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass through their touching point, that is point P. Or OPM is one straight line. Again, OPM, according to this rule 10, is one straight line. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, we have an external notch between this semicircle and this quarter circle. That is to say, they touch each other externally at this point, point S. Therefore, we can implement rule 10. The center of this semicircle is 0 at point O. The center of this quarter circle is 0 at point C. And the straight line that connects the centers together is of course the straight line OC. And according to rule 10, the straight line OC must pass through their touching point, that is point S. Again, the straight line OC must pass through point S, that is their touching point. Or OSC is one straight line. Again, OSC is one straight line. So we join points O and C together by straight line, and according to rule 10, the straight line OC must pass through point S, that is their touching point. So it's very easy to see that the straight line OC passes from point S, that is their touching point. And therefore, the length of line segment OC of the straight line OC must be equal to OS plus SC. Why? Because OSC is one straight line. So OC equals to OS plus SC. So I write it down. OC, according to rule 10, OC equals to OS plus SC. So OC equals to OS. What is the definition of line segment OS? Line segment OS starts from point O, that is the center of the semicircle, and then at point S, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore, OS is the radius of this semicircle, is equals to x over 2 units in its length. So here, OC equals to OS, that is x over 2, plus SC. What is the definition of line segment SC? Line segment SC starts from point C, that is the center of the quarter circle, and ends at point S, that is the point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, SC is the radius of this quarter circle, that is equal to x according to our definition. So SC equals to x. So here, OC equals to x over 2 plus SC, that is x. So total OC equals to x plus x over 2, that is 1.5x, or 3 over 2 times x units in its length. In total, we shall find out that OC equals to 3 over 2 x units in its length. So this is the hypotenuse OC of the right triangle ODC, and it is equals to 3 over 2 times x units in its length. In the next step, I'll copy the right triangle ODC, this right triangle ODC in the new page, and we will implement the Pythagoras theorem on this right triangle ODC. But before that, we know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5. So I write it down. Side DC of rectangle ABCD equals to 5 units in its length. So in the next step, I'll copy this right triangle ODC in a new page, and we will implement the Pythagoras theorem on this right triangle ODC. Here by PT is the version for Pythagoras theorem. Side OD equals to x over 2 units in its length. We just right now found out that side DC equals to 5 units in its length, and the hypotenuse OC equals to 3 over 2 times x units in its length. So actually, this is the right triangle ODC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle ODC, OC square equals to OD square plus DC square. Again, OC square equals to OD square plus DC square. So I write it down. OC square, that is the square of the hypotenuse, equals to OD square plus DC square. The hypotenuse OC equals to 3 over 2 times x units in its length, therefore OC squared is 3 over 2 times x squared. That actually equals to 9 quarters times x squared, and it is equals to OD squared. OD is x over 2, therefore OD squared is x over 2 squared, that is actually x squared over 4. Plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total we found out that 9 quarters times x squared equals to 1 quarter x squared plus 25. Here we subtract x squared over 4 from this equation, and we get that nine quarters times x squared minus 1 quarter x squared equals to 8 quarters x squared. That is equals to 25. Eight over 4 is 2, so in total this expression equals to 2x squared. So 2x squared equals to 25. Here we divide this equation by 2, and finally we get that x squared equals to 25 over 2. X squared equals to 25 over 2. Here we take a root out of this equation, and finally we get that x equals to the square root of 25, that is 5, over square root of 2. So in conclusion we found out that x squared equals to 25 over 2, and x equals to 5 over square root of 2 units in its length. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Repeat again, I shall find out that the area of this green shape equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So what is the area of rectangle ABCD? Actually the area of any rectangle equals to the length of the rectangle times the width. The length of rectangle ABCD is AB, that is 5. The width is BC, that is x. So in total, the length times the width is 5 times x. So the area of rectangle ABCD is 5x. So write it down. I shall find out that the area of this rectangle ABCD equals to 5x square units minus the area of the semicircle. What is the area of this semicircle? We know that the radius of this semicircle is x over 2. Therefore, the area must be equal to pi times the radius squared divided by 2. So it is pi times x over 2 squared divided by 2. So I write it down. I shall find out that the area of the semicircle equals to pi times the radius squared divided by 2. The radius is x over 2, and therefore the radius squared is x over 2 squared divided by 2. So in total, the area of the semicircle equals to pi times x over 2 squared divided by 2 minus the area of the quarter circle. What is the area of this quarter circle? The area of this quarter circle equals to the area of the circle over 4. We know that the radius of the circle is x. Therefore, the area of the circle is pi x squared. And therefore, the area of the quarter circle must be equal to pi x squared over 4. So the area of the quarter circle equals to pi x squared over 4. So actually, the value of this expression is equals to the area of the green shape. So this expression equals to 5x minus, here we have x squared over x over 2 squared is x squared over 4. So in total, the value of this expression will be equal to pi times x squared over 4 multiplied by 2 minus pi x squared over 4. So the area of the green shape equals to 5x. Here we have minus pi x squared over 2 times 4. 2 times 4 is 8. So in total, this expression equals to minus pi x squared over 8. Minus pi x squared over 4. Here we multiply both the numerator and the denominator of this expression by 2, and we get that it will be equal to 2 pi x squared over 8. 2 pi x squared over 8. So in total, we can find out that the area of the green shape equals to 5x minus pi x squared over 8 minus 2 pi x squared over 8. So the area of the green shape equals to 5x. Here we have minus pi x squared over 8 minus 2 pi x squared over 8 is minus 3 pi x squared over 8. So in total, we can find out the area of the semicircle equals to 5x minus 3 pi x squared over 2. It is actually x squared over 8, of course. The denominator we have 8. So it is 3 pi x squared over 8. the area of the green shape in total equals to 5x minus 3 pi x squared over 8. So, but we already found out that x equals to 5 over square root of 2 units in its length, and x squared equals to 25 over 2. So we can substitute x in this expression by 5 over square root of 2, and x squared in this expression by 25 over 2. We'll do it now, and we get that the area of the green shape in total equals to 5 times x, and x equals to 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. 25 over 2. So in total we found out that the area of the green shape equals to 5 times 5 is 25, so in total this expression equals to 25 over square root of 2. Here we have in the numerator 3 pi times 25 is 75 pi, so it is minus 75 pi, divided by 8 times 2 is 16. So in total this expression equals to 75 pi over 16. So we found out that the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units, or in terms of numbers it is equals to 2.95 square units. And that is the answer to the question. Repeat again, we found out that the area of this green shape equals to 2.95 square units. So in the next step, we summarize the lecture. We'll start with the first question, of course. In the first question, our mission is to find out the area of this semicircle that is located inside this quarter circle AOB. So in the drawing we have a quarter circle AOB. We know that the radius of this quarter circle AO equals to 5 units in its length. Inside this quarter circle AOB we have this semicircle, and our mission is to find out the area of this semicircle. So first of all, we defined the center of this semicircle. This point is point C. We defined the intersection point between the semicircle and the quarter circle. This point is point F. We defined the other intersection point between the semicircle and the quarter circle. This point is point G. Likewise, we defined the point of tendency of tangent OB with this semicircle. This point is point L. And finally, we define the point of tendency of tangent AO with this semicircle. This point is point H. In addition, we know that the radius of the quarter circle equals to 5. So we define the radius of the semicircle as x. Therefore, if we join points C and G together by a straight line, actually we have already points C and G. CG is the radius of the quarter circle, that is x. CF is also the radius of the quarter circle. It is equal to x according to our definition. In the next step, we join points C and L together by a straight line. CL is of course the radius of the semicircle, that is equal to x units in its length. According to our definition, we join points C and H together by a straight line. CH is also the radius of the semicircle, that is equal to x. By doing these constructions, we can deduct quadrilateral CHOL. Inside quadrilateral CHOL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral equals to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral CHOL, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So So we learned to this quadrilateral CHOL is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CHOL, side CH must be equal to the opposite side OL. But CH is x, therefore OL must be also equal to x. Likewise, according to the same rule, in the same rectangle CHOL, side CL must be equal to the opposite side OH. But CL is x, therefore OH must be also equal to x. So actually found out that quadrilateral CHOL is not a rectangle but a square because all of its sides are equal to each other. Each side of this square equals to x. In the next step, we join point C and O together by straight line. By doing this construction, we can do the right triangle CLO. The right triangle CLO is also an isosceles triangle because side CL equals to side LO, they are both equal to x. In the next step, I copied this right and isosceles triangle CLO in a new page, and we implemented the Pythagoras theorem on this right and isosceles triangle, triangle CLO. This is the right and isosceles triangle, triangle CLO, that I got from the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle CLO is CO, therefore the square of the hypotenuse is CO square, and CO square equals to CL square plus LO square. Again, CO square equals to CL square plus LO square. CO is the missing side, so we leave it as it is. So CO square equals to CL square. CL is x, therefore CL square is x square plus LO square. LO is also x, therefore LO square is x square. So in total CO square equals to x square plus x square, that is 2x square. So CO square equals to 2x square. Here we took a root out of this equation and finally found out that the missing hypotenuse CO equals to the square root of 2 times x units in its length. So here CO equals to the square root of 2 times x units in its length. So we know that point O is the center of the quarter circle. So from this point that is the center of the quarter circle, we have line segment OC. Line segment OC bisect chord FG. Why line segment OC bisect chord FG? Because of the fact that CF equals to CG. So line segment OC divides chord FG into 2 halves. Each half equals to x. And whenever you have from the center of the circle a line segment that bisects a chord, you can implement rule 7. So I'll teach quickly rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects a chord, then the line segment is also perpendicular to that chord. So in the drawing we have a circle, and this is point O, that is the center of the circle. From the center of the circle, that is to say from this point O, we have line segment OM that bisects chord AB. That is to say MA equals to MB. And because of the fact that line segment OM bisects chord AB, line segment OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule 7. So whenever you have a line segment that bisects, whenever you have a line segment that is drawn from the center of the circle and bisects a chord, then the line segment will be also perpendicular to that chord. So you can actually implement rule 7 in our drawing. Why? Because in our drawing we have line segment OC that exists from point O, that is the center of the quarter circle, and it bisects chord FG. That is to say, it divides chord FG into 2 halves. Each half equals to x. And therefore, according to rule 7, line segment OC will be also perpendicular to chord FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 7. In the next step, we join points O and F together by straight line. We know that the radius of the quarter circle equals to 5, because AO equals to 5. So what is the definition of line segment OF? Line segment OF starts from point O, that is the center of the quarter circle, and ends at point F, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OF is the radius of this quarter circle, that is equal to 5. In the next step, I copied this right green triangle CFO in a new page, and we implemented the Pythagoras theorem on this right green triangle, triangle CFO. So this is the right wing triangle CFO that I copied from the original drawing. Side CF equals to x, this is the radius of the semicircle. We have already found out that CO equals to the square root of 2 times x units in itself. And we know that FO is the radius of the quarter circle, this is equal to 5. So according to the Pythagoras theorem, in this right triangle CFO, FO squared, that is the square of the hypotenuse, must be equal to CF squared plus CO squared. Again, FO squared equals to FO squared equals to CF squared plus CO squared. FO, the hypotenuse FO is 5, therefore FO squared is 5 squared, that is 25. And it is equals to CF squared. CF is x, therefore CF squared is x squared plus CO squared. CO is square root of 2 times x, therefore CO squared is square root of 2 times x squared, that is 2x squared. So in total, we actually found out that 25 equals to x squared plus 2x squared. 25 equals to x squared plus 2x squared, that is 3x squared. So 25 equals to 3x squared. Here we divided the equation by 3, and we found out that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. The area of the semicircle equals to the area of the circle over 2. And the radius of the semicircle is x. Therefore, the area of the semicircle in total must be equal to pi x squared over 2. So the area of the semicircle, the area that we are looking for in this question, equals to pi x squared over 2. X is the radius of the semicircle, of course. So it is pi over 2 times x squared. And we just write down found out that x squared equals to 25 over 3. So we can substitute x squared in this equation by 25 over 3. We did it. And we actually found out that the area of the semicircle in total equals to pi over 2 times x squared. And x squared is 25 over 3. So in total, the area of the semicircle equals to 25 pi over 2 times 3, that is 6. So in total, the area of the semicircle equals to either 25 pi over 6 square units, or in terms of numbers, the area of this semicircle equals to 13.09 square units. So we finished with the first question. In the next step, actually present it to the second question and solve the second question. Our mission in the second question is to find out the area of this vein shape. So in the drawing we have a rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in itself. In addition, inside this rectangle ABCD we have this semicircle and this quarter circle. Again, our mission is to find out the area of this vein shape. So first of all, we define the radius of this quarter circle as x. Therefore, BC, that is the radius of the quarter circle, equals to x according to our definition. We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD must be also equal to x. AD is not only one side of rectangle ABCD, but AD is also the diameter of the semicircle. So we know that the diameter of the semicircle AD equals to x. If the diameter AD equals to x, the radius must be equal to half of it. That is to say, the radius of this semicircle must be equal to x over 2. The center of this semicircle is at point O. So the radius OA equals to x over 2, and the radius OD also equals to x over 2 units in its length. We also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC, but AB is 5, therefore DC must be also equal to 5. We also know that all the angles inside the rectangle are right angles. So this angle must be equal to 90 degrees in its size. Here we have an external match between this semicircle and this quarter circle. That is to say, they touch each other externally at this point S. Whenever you have an external match between two circles or semicircles, you can implement rule 10. So I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together passes for their touching point. So in the drawing we have two circles. and they touch each other externally in this point P. So they have an external edge between them at point P. The center of this circle is here at point O. The center of this circle is here at point M, and the straight line that connects the circles together is of course the straight line OM. And according to this whole 10, the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this whole 10. So we can actually implement all 10 in our drawing. Why? Because in our drawing we have an external edge between this semicircle and this quarter circle. That is to say, they touch each other externally at this point S. So according to rule 10, we know that the center of this semicircle is at point O. The center of this quarter circle is at point C. The straight line that connects the centers together is of course the straight line OC. And according to rule 10, the straight line OC must pass through point S, that is their touching point. Again, the straight line OC must pass through their touching point, that is point S actually. Or OSC is one straight line. Again, OSC is one straight line according to rule 10. If OSC is one straight line, it means that OC must be equal to OS plus SC. Again, OC must be equal to OS plus SC according to rule 10. So OC equals to OS. OS is the radius of this semicircle, that is x over 2, plus SC. SC is the radius of this quarter circle, that is equals to x according to our definition. So in total, OC equals to x over 2 plus x, that is 1.5x or 3 over 2x. So the hypotenuse OC of this right triangle ODC equals to 3 over 2 times x units in its length. In the next step, I copied this right triangle ODC in a new page and implemented the Pythagoras theorem in this right triangle ODC. So actually, this is the right triangle ODC that I copied from the original drawing. Again, the hypotenuse OC equals to 3 over 2 times x units in its length. OD equals to x over 2 and DC equals to 5. So according to the Pythagoras theorem, in this right triangle ODC, OC square equals to OD square plus DC square. OC is 3 over 2 times x, and therefore OC square is 3 over 2 x squared. That is actually 9 quarters of x squared, and it equals to DO squared. DO is x over 2, therefore DO squared is x squared over 4 plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total we can find out that 9 quarters times x squared equals to 1 quarter x squared plus 25. Here subtracted x squared over 4 for this equation, and finally found out that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared, and it is equal to 25, because x squared over 4 minus x squared over 4 is 0, so we left only with 25. So 8 quarters x squared equals to 25. 8 over 4 is 2, so in total this expression equals to 2x squared, and 2x squared equals to 25. Here we divided this equation by 2 and finally found out that x squared equals to 25 over 2. Here we took a root out of this equation and finally found out that x equals to the square root of 25, that is 5, over the square root of 2. So in total we found out that x squared equals to 25 over 2, and x equals to 5 over the square root of 2 units in its length. Our mission is to find out the area of this green shape. So what is the area of the green shape? For the drawing it is very easy to see that the area of this green shape equals to the area of the rectangle ABCD minus the area of the semicircle minus the area of this quarter circle. I repeat again, the area of the green shape in total equals to the area of the rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So the area of the semicircle equals to the area of the rectangle ABCD. What is the area of rectangle ABCD? We know that the area of any rectangle equals to the length of the rectangle times the width. The length AB is 5, the width BC is x, and therefore the length times the width is 5x. So the area of rectangle ABCD is 5x. 5x square units. The area of rectangle ABCD is 5x square units minus the area of the semicircle. What is the area of this semicircle? We know that the radius of this semicircle is x over 2. And therefore the area of the semicircle must be equal to pi times the radius square over 2. So it is pi times x over 2 squared divided by 2. So in total we can find out that the area of the semicircle equals to pi times x over 2 squared divided by 2. Minus the area of the quarter circle. What is the area of the quarter circle? you know that the radius of the quarter circle is x. And therefore, the area of the quarter circle must be equal to pi x squared over 4. So the area of the quarter circle equals to pi x squared over 4. So in total, the value of this expression is equal to the area of the green shape. So this expression in total equals to 5x, and here we have pi x over 2 squared equals to x squared over 4 divided by 2. So in total this expression will be equal to pi x squared over 4 times 2. This pi x squared over 4 times 2. Minus pi x squared over 4. 4 times 2 is 8, so in the numerator of this expression we have 8. So in total we should found out that the area of the green shape equals to 5x, and this expression in total equals to pi x squared over 8. And here we have pi x squared over 4. We multiplied both the numerator and the denominator of this expression by 2. After we multiply it by 2, this expression equals to 2 pi x squared over 4, or minus 2 pi x squared over 4. Minus 2 pi x squared over 4. So the area of the green shape equals to 5x minus pi x squared over 8 minus 2 pi x squared over 8. Minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total, the area of the green shape equals to 5x minus 3 pi x squared over 8. But we already found out that x equals to 5 over square root of 2, and x squared equals to 25 over 2. Therefore, we can substitute x in this equation by 5 over square root of 2, and x squared in this expression by 25 over 2. We did it, and we actually found out that the area of the green shape in total equals to 5, and x is 5 over square root of 2, minus 3 pi over 8 times x squared, and x squared is 25 over 2. So in total, the area of the green shape equals to, here we have 5 times 5, this is 25, so in total this expression equals to 25 over square root of 2, minus, here we have 3 pi times 25 is 75 pi. So in total, in the numerator we have 75 pi. In the denominator we have 8 times 2, that is 16. So in total, this expression equals to 75 pi over 16. So we should found out that the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units. So in terms of numbers, the area of this green shape, the value of this expression is actually in total is 2.95 square units. Again, the area of this green shape equals to 2.95 square units. Okay, thank you very much.